Hello everybody, welcome to BYJU'S. This is Abhilash here. We are looking at NEET 2020 questions. So we have already done inorganic chemistry questions before. If you have missed that part, definitely catch up on that as well. As I was telling you, we are discussing NEET 2020 questions because whenever you are going to sit for an exam, it is always better to know what happened in previous exams so that you get a fair enough idea about how that paper is going to be like. Right. So as far as chemistry itself is concerned, we have physical, organic, inorganic, which has almost equal weightage every year, and this year was no exception. We had 15 questions each in physical, organic and inorganic. What we are going to do today out here is to look at the physical chemistry questions that were asked, right? So obviously we won't be solving all of these questions in one go. The point is that as far as BYJU'S is concerned, we wanted to see to it that whenever we are discussing a question, we don't just give you the answer and a quick formula to solve this and run away. No, we try to explain the background behind it, some bit of concepts behind it as well, just in case even if you have like kind of feeling rustic about it, you don't really remember it entirely, we'll still brush concepts up a bit, right? Obviously not the whole chapter and everything related to that, but yeah, as much as is required for you to recollect enough so that we can solve the question very efficiently, right? So yeah, chapter wise, as far as the paper itself was concerned, as I was telling you, 15 questions each were there. A total of 15 questions were there in physical as well, which had a nice spread this year, right? So if you see mole concept, atomic structure, gaseous state, thermodynamics, equilibrium, solid state, solutions, electrochemistry, chemical kinetics, surface chemistry, almost one question each from almost every chapter was taken up. And like two questions are there in like the important chapters as well, right? So electrochemistry from 12th, solutions, electrochemistry, chemical kinetics all had two questions each. Surface chemistry also we had one question. Solid state, again equilibrium we took it together. Even thermodynamics, thermodynamics and equilibrium, I would say combined, is one of the most important parts of 11th physical chemistry. They were also represented. Gaseous state, simple question was there based on Dalton's law. Atomic structure and mole concept also had one question each, right? Simple questions. We have heard this before that you never get like too tough questions as far as NEET is concerned, right? So the idea is that as far as questions are concerned, they were not too tough or anything, relatively simple questions. Anyways, physical chemistry is all about calculations and all. None of the calculations were so tough that you won't be able to, you end up spending a lot of time on it and you don't get time to think. That was not the case, right? With this, let's start with the questions. See, now let's look at the question. Let's read the question first. The mixture which shows positive deviation from Raoult's law is, right? So this is from solutions. We are asked about which one is showing positive deviation from Raoult's law or deviation from ideality, right? So the options given are benzene, toluene, acetone, chloroform, chloroethane, bromoethane, and ethanol and acetone, right? So what is the idea here? What do you mean by Raoult's law? What do you mean by ideal solution? We should understand a bit about this briefly. Let's talk about this also. Raoult's law says that as far as the vapor pressure that is there above a liquid, when you have like two liquids forming an ideal solution, and the vapor pressure individually of these gases above the surface of the liquids is going to be proportional to the mole fraction of that component in the liquid phase. This is the general idea behind Raoult's law, right? So whatever is the vapor pressure of one gas, that will be proportional to the mole fraction of that liquid in the solution. So two liquids I take, number of N1 moles, N2 moles, I add these, mole fraction will decide the partial pressure, right? The vapor pressure of that individual component gas. So we have already discussed this. The partial vapor pressure of each component is directly proportional to the mole fraction of that particular component present in the solution. So PA is proportional to XA, PB is proportional to XB, and then we can individually say that we end up getting PA to be equal to P naught A into XA and BB equal to P naught B into XB. How do you get this? Think of when you have XA equal to 1, right? That is pure A. So obviously P naught, the total vapor pressure should be equal to P naught A, right? So obviously you can say this you can say that P total will be equal to some K into XA, let's say K1 into XA plus K2 into XB, and when XA is equal to 1, total pressure should be P naught A, so we will get K1 equal to P naught. The proof behind this, obviously, I'm sure you are very comfortable with. So when you take these individual, all of these components are also defined. XA is mole fraction of A, PA is partial pressure of A alone in that vapor mixture, PB is that of B alone, P naught is what you call as the pure vapor pressure of A at that temperature, right? So if A alone was present, what is the vapor pressure? Similarly, P naught B is pure B. If it was present alone, what will be the partial pressure? That is our P naught B, and the sum of these two, PA plus PB, gives us P total. So P naught A into XA plus P naught B into XB. Wherever this is valid, we say that such a solution is following Raoult's law and it is an ideal solution, right? So yeah, we have already discussed about this. Let's go forward. What is ideal and non-ideal? So as I was telling you, when this Raoult's law is entirely valid, directly valid, we say that the solution can be called as an ideal solution. It follows Raoult's law. And the non-ideal solution is one where Raoult's law is not valid, right? Raoult's law is not followed. So you can say that Raoult's law is valid in an ideal solution, not valid in a non-ideal solution. So yeah, so what happens in an ideal solution is that A and B are so much similar to each other. This is a typical thing that you see. Where all do you get ideal solutions? How do you identify an ideal solution? If the substances you know have very much similar properties, very much similar nature as such, you can say, okay, let's say for example propane and propane is of course in a gas form, but yeah, let's say that if you are comparing something like propane and butane, these are like very similar substances, right? So benzene and toluene, very similar in nature, right? Chloroethane, chloromethane, something like this, right? So wherever the substances are very much similar to each other, their natures are very much similar to each other, we end up getting ideal solution where the enthalpy change on mixing the solutions, there is no difference between basically AA attraction and BB attraction much. So AB attraction is also similar to this. That is the case. A and B are the two components. Then we say that it is an ideal solution. There is no volume change on mixing either. There is no energy change, enthalpy change on mixing these solutions. There is no volume change either. 10 ml, 20 ml, you get 30 ml. Such a case is what you call as an ideal solution, right? What we say is that AA attraction, BB attraction are also similar and they are also similar to AB attraction. Then we say that yeah, this is also important. They have to be also similar to each other. Then we say that intermolecular attractive forces that are there, if they are pretty much similar to each other, we end up getting an ideal solution, right? Examples would be, as I was telling you, benzene, toluene, very much similar to each other. No, polarities and all are not there, and like organic substances, similar like kind of looking electron clouds and similar shape, somewhat similar. So we say that okay, these will form what you call as ideal solution. So in these, as I was telling you, there what we end up seeing is that their Raoult's law graph will turn out to be perfect, right? So if I'm plotting individually PB and PA, and then we say that okay, the net total pressure over this mixture, depending upon what is the mole fraction of A and B, you can plot something like this. You see that the sum of this and this at any point will be equal to this, right? So basically this height plus this height will be equal to that. This is basically your so XA equal to 1 would mean that only A is there, the pressure there is P naught A, XB A equal to 0 or XB equal to 1, pure B is there, P naught B, and the sum of these two is your total pressure, and you end up getting something like this. If this is followed, we call it as an ideal solution. What do you mean by non-ideal? When the vapor pressure is not equal to what is predicted by Raoult's law. Within that, we speak of positive deviation, negative deviation, right? So vapor pressure is either higher or lower than what is predicted by Raoult's law. In that case, we call it as positive deviation if there is higher vapor pressure than what is expected, and if it is lower than what is expected, then we speak of what we call as negative deviation, right? So here what we see is that vapor pressure, in case of positive deviation, there is higher vapor pressure than what is expected, right? And in negative deviation, we see that there is lower vapor pressure than what is expected. Let's look at the positive deviation case. So as I was telling you in the graph, according to Raoult's law, what should have been your PA is what is plotted, PB is what is plotted here, and you're getting the actual graph to be something like this. What does that tell you? The presence of A is some way or the other disturbing B so much that B wants to jump out of the solution, right? Same is the case with your PA as well. So PA was expected to be this, but we end up getting slightly higher value than this because the presence of B is so irritating to A that A doesn't want to remain in liquid, right? So AB attraction. Suddenly when A was alone present, or A was all surrounded by A, there is attraction between A, they are happy. But suddenly when you add B, B is also present in between, right? So A sees, okay, there is this B here, I'm not attracted to B and I'm going to stay away. That is something that creates this extra vapor pressure because there is less attraction and their tendency to jump from liquid to vapor state increases. This is positive deviation, and we end up getting, this should have been what was there according to Raoult's law, the sum of the individual pressures, but we end up getting something else altogether. This is what we call as positive deviation. When will this happen? When AB attraction is not that effective, AB, AA, BB attractions and all of these are not equal, and the AB attraction is less than what is there between AA and BB, then we end up seeing this happening. When will this happen? When there are differences, right? So when they are very much different in nature, their attraction, interparticle attractions and all are different, we end up getting something like this, right? So where is negative deviation? When vapor pressure is less than what is predicted by Raoult's law, what is going to happen here? The B pressure was supposed to be this, but actual observed is the red one, which is less than what is predicted by Raoult's law. Same with the A. It was supposed to be this dotted yellow line, but we are seeing this red line because the partial pressure of A is for some reason less than what it was expected if pure A was there. What does that mean? Why is this happening? When A was sitting, A was experiencing attraction from A. A is okay with this attraction. Okay, this is fine. But suddenly B is here and B has a lot more attraction for A. So A is like stuck to B. A can't escape, right? So the presence of B is causing so much chaos in A that A is attracted to B now and is not interested in jumping out of the solution into vapor phase. So greater AB attraction than what is there between AA molecules and BB molecules, we end up seeing this. So the, like for example, in case of something like acetone chloroform mix, where you end up seeing that individually neither of these had any hydrogen bonding, but because when they are mixed together there is hydrogen bonding happening. So this acetone chloroform is a very famous example for this negative deviation. They have differences in their they are probably different substances altogether, different type of substances, plus there is a case like something like hydrogen bonding or something coming into picture, extra unexpected attraction coming into picture, which is causing this negative deviation, right? So yeah, the net total pressure will be less than what is predicted. The individual properties, we have discussed all of these. So let's move forward to what is a few examples of positive and negative. We have already discussed the idea here. Positive deviation example would be acetone, ethanol, water. So ethanol would have been happy to bond with each other. This acetone is different and is like coming into the solution, and now ethanol is not very easily bonding to itself, like, you know, more compact kind of way. Probably they could have arranged themselves. That is not happening. So we end up getting positive deviation. Water methanol, same story. Water ethanol, same story. CCl4 toluene, see, different, right? CCl4 is like a giant heavyweight tetrahedral molecule that is there, and your toluene is different. Toluene is like benzene plus your methyl group, right? So they have like drastic differences between them. If only toluene was present, their areas and all, better packing and all would have been there, better attraction would have been there, but the CCl4 tetrahedral is coming in between and wasting space, right? And CCl4 also was like, okay, if we were alone present, we would have nicely arranged like this and in a very regular fashion, and we would have been attracted to each other better. But suddenly this toluene is coming, like, a thingy that is like disturbing the whole good arrangement and good attraction that could have been there. So we end up getting positive deviation. Negative deviation, as I was telling you, one obvious example is this acetone chloroform, very famous example. Benzene chloroform, similarly nitric acid chloroform, water and nitric acid, similar examples where some unexpected new crazy attraction is coming into picture, and that is causing negative deviation, right? So in our question, what did we have? Like we had benzene, toluene, acetone, chloroform, chloroethane, bromomethane. So look at this. So benzene and toluene very much similar to each other, ideal solution. Chloroethane, bromoethane very much similar to each other, ideal solution. Acetone, chloroform, we are seeing negative deviation, right? Standard example. So that is why it was a simple question. Even if you are not very sure about this, you would still get the answer, right? So ethanol and acetone, we end up seeing positive deviation, which was exactly what was asked in the question, right? So the question said which shows positive deviation from Raoult's law in this question, right? So looking at the options, we can obviously see that the correct answer is our D option, right? Ethanol plus acetone. Let's look at the next question. It says an element has a body-centered cubic structure, BCC structure, with an edge length of 288 picometer. The atomic radius is. The edge length A is given to us, and we have been asked, we have been told that it is a BCC structure, body-centered cubic structure. We have been asked about the radius of the atom, right? So this is an elemental substance in BCC arrangement, and we have to see the relationship between the atomic radius and the edge length. How are they related? So what exactly is a BCC? For that, let's see this. So as far as body-centered cube is concerned, like in a cubic kind of situation with a atom at the body center, right? So what happens here is, even though we normally draw it like this, right? So we draw it like this, but yeah, the idea is that they are touching each other, right? So along, what you call as your body diagonal. In BCC unit cell, atoms lying along a body diagonal touch each other. What do you mean by that? Put all of these atoms, right? And there is this, atom at the body center which is touching this diagonally opposite corners. So in this cubic kind of shape, the diagonally opposite ones along the body center will be touching each other. We can see that here very clearly. So this is our edge length A, right? So this is our edge length A. So if I'm looking at the diagonal of any face, that is called a face diagonal, and that will be root 2A length. You can obviously understand here A and A are the two, they are at 90 degrees to each other, and then you have your face diagonal which will be at root 2A. And as far as the next one is concerned, where your body center atom is lying, that is what you call as your body diagonal, and that has a length of root 3A, right? So when you are looking at your body centered cubic kind of an arrangement, what is happening is, even though we are drawing it like this far away from each other, the point is that these atoms are the three that are touching each other, right? So you can see that these atoms are touching along the body diagonal, and it has a length equal to root 3A, right? So what can you say? I mean, when you're looking at the shape as such, as I was telling you, these were the atoms that were touching each other, right? So this is the one end, and this is the other diagonal end of the cube, and this is radius R, this is radius 2R, and this is radius R again. So this length, body diagonal length, is equal to 4R, right? So we can say that length of body diagonal is root 3A, 4R will be equal to root 3A, so R is supposed to be equal to root 3A by 4, right? So here A was already given to us as 288 picometer, so our R will be equal to root 3 into A by 4, root 3 into 288 picometer was the value that was given to us anyways. So what is the correct answer here? Radius will be equal to root 3 by 4 into 288 picometer, which is our D option. So let's read the question. It says the hydrolysis of sucrose is given by the following reaction: sucrose plus H2O, reversible reaction, glucose plus fructose. If the equilibrium constant KEQ is 2 into 10 to the power 13 at 300 Kelvin, then the value of delta G naught for the reaction at the same temperature will be, right? So what do you mean by your what is the relationship between this equilibrium constant and your delta G naught? This is a simple direct formula that we had to use. Of course, the options are given in such a way that you don't have to actually calculate the value. That would have been really terrible. But yeah, what is the theory behind this? What we speak of is the relationship between delta G naught and Q to get the relationship between delta G naught and K equilibrium, right? So as far as a reversible reaction is concerned, we say that a reversible reaction is spontaneous when delta G is less than 0, non-spontaneous when delta G is greater than 0, and delta G is equal to 0 when the reversible reaction is at equilibrium, right? So let's look at a generic reaction like this, A plus BB giving you CC plus DD, reversibly, gives free energy change when it is positive. As I was telling you, we say that the reaction is non-spontaneous. If it is less than 0, we say that it is spontaneous, right? Spontaneous means it is still going towards equilibrium. It has not attained equilibrium. When delta G becomes equal to 0, we say equilibrium is attained, right? So here the relationship between delta G gives energy under any condition and delta G naught. What is delta G naught? Delta G under standard condition. If the reaction mixture is there and you have all the substances in standard state. What do you mean by that? If I have solutions, it should be 1 molar concentration of substances. If I have gases, it should be 1 bar pressure. Then we say that. Or if you have like some pure solid or liquid, it should be standard state under 1 bar. Then we call the reaction mixture, that condition, to be in standard condition. Delta G gives free energy under standard conditions is delta G naught. Under any condition, whatever condition you are in, that is called delta G, and they are related by this equation. Delta G is delta G naught plus RT ln Q, where Q is the reaction quotient under that particular conditions where we are speaking about delta G. Now, as I was telling you, when delta G becomes 0, we say the system has attained equilibrium, right? So, what does that tell you? Delta G naught plus RT ln Q at equilibrium will be equal to 0. But Q at equilibrium is exactly what we call as equilibrium constant, right? So, we get this whole thing to be equal to 0, which means we will get delta G naught is equal to minus RT ln K equilibrium. So, we have been given K equilibrium. We have been given the temperature, we know the value of R. Obviously, we just have to put them and see in this particular given question what was the delta G naught. So delta G naught is minus R is 8.314 joule per mole per Kelvin. Temperature was 300 Kelvin. Ln ln of K being 2 into 10 to the power 13. Normally we write the minus 2.303 in RT log K equilibrium equation, but yeah, point is that ln K, because here in the options also we were given things in ln form only, right? So equilibrium constant is 2 into 10 to the power 13, and we had to find out the option, right? So looking at it, I am looking for minus RT ln K. Where do I see that? Minus 8.314 and 300 and ln 2 into 10 to the power 13. This is something I can obviously see in D option. Our final answer is D. Okay, now let's look at the next question. It says a mixture of N2 and argon gas in a cylinder contains 7 gram of nitrogen and 8 gram of argon. If the total pressure of the mixture of gases is 27 bar, the partial pressure of nitrogen is, right? Simple question from gaseous state, simple question based on Dalton's law. So Dalton's law of partial pressure is what we are going to use here. We have been given a mixture where there is nitrogen and argon. Individual weights are given to us, right? So from weight we can find number of moles very easily. Once we know the number of moles, we can find partial pressure, mole fraction individually. Once we know mole fraction into total pressure, which is given to us as 27 bar, we should be able to get the individual partial pressures, right? So what is partial pressure? Partial pressure is pressure exerted by one gas component, right? So if you have a gas mixture, non-reacting gases, gas mixture, the individual pressure exerted by one particular gas is called its partial pressure. And let's say we have some mixture like the one yellow gas, one red gas, and then we mix, there is another blue gas also, and we mix all of these. What we see is that the total pressure in this case will be equal to pressure due to yellow plus pressure due to red plus pressure due to blue. This is obvious, but a more interesting fact that Dalton's law says is that this partial pressure exerted by blue, yellow and red is the same as what they would have exerted if they were present alone. See, gases are too tiny, way less attraction. One doesn't care about the other unless and until they can react with each other. H2 and Cl2 can react. There this won't hold. Ammonia, HCl, they can react. This won't hold true. But if the gases don't react with each other, they don't care. They'll just run around, collide, whatever. Whatever pressure was exerted by, for example, red, when the other two are not there, that will be exerted by red even now. This is the idea behind Dalton's law of partial pressure, right? So the individual pressure that would have been exerted by the gas if the gas alone was present in a mixture is an alternate way of looking at what you call as partial pressure. Here we had three components, N1, N2, N3 are, let's say, the number of moles. Then we can say that, okay, N1 upon N1 plus N2 plus N3 is mole fraction of 1, N2 upon N1 plus N2 plus N3 is mole fraction of 2, and N3 upon N1 plus N2 N3 is mole fraction of 3, and mole fraction into total pressure individually will give me the partial pressure of each of these gas. This is the idea. So your P1 is, for example, N1 RT by V, right? This is what I was telling you. It's as if only one is there in the mixture. It doesn't. So PV equal to nRT basically is individually valid for each gas. This is what is written here in this statement indirectly. So P3V is equal to N3RT, right? So PV equal to nRT is valid for the whole gas mixture. P1 plus P2 plus E3 is equal to N1 plus N2 plus N3 into RT, and also for the individual gases in a mixture, right? So P total is P1 plus P2 plus V3, which is equal to this, and we can say that total number of moles is N1 plus N2 and all. When we take P1 by P total or P2 by P total and all, we will get N1 by N total, N2 by N total and all, which means it is equal to mole fraction. So total pressure is sum of individual partial pressures of the component gases as long as they are non-reacting. That is important. Then we say that, okay, like for example, let's say we have oxygen and nitrogen, maximum present in air, right? Will oxygen and nitrogen react with each other? If you want to think about it, think that air is just this. If reaction was to happen, it would have been happening, right? So approximately the pressures that you end up seeing in atmosphere, right? So almost at sea level you would be seeing approximately around 160 mm, 159 mm of mercury of oxygen, around 593 mm of 593 mm mercury of your nitrogen, and the sum of these two is roughly approximately the total pressure as well, right? So atmospheric pressure is more or less entirely pressure of nitrogen plus oxygen. Other gases are there, but relatively small quantities, right? So yeah, this is about Dalton's law specifically. Yeah, so this also we had discussed, right? So P1 by P total turns out to be N1 by N total, which is mole fraction of 1. Similarly, P2 by PT, you can see here is given as X2, and in general Pn by Pt will be equal to mole fraction of the nth component, right? So here what did we have? We just had simple nitrogen and argon. Nitrogen gas weight was given, argon weight was given. Obviously we know that nitrogen molar mass is 28 grams per mole and argon 40 grams per mole, right? So because total pressure is also given, individual weights are given, if I manage to find the number of moles, I should be able to get mole fraction. Simple, right? Moles of nitrogen will be how much? We had like 7 gram, 28 grams per mole, so 0.25 or 1 by 4 is your moles of nitrogen. Similarly, argon we had 8 grams and molar mass is 40 grams per mole, monoatomic, right? So 8 by 40 is 1 by 5, 0.2, right? So total pressure was anyways given to us as 27 bar. So mole fraction into total pressure should give me the partial pressure. So mole fraction is number of moles by total number of moles. Mole fraction of nitrogen will be how much? Number of moles of nitrogen, we got it to be how much? 1 by 4, right? So 0.25 divided by 0.25 plus 0.2 or 0.25 by 0.45. You can see this is what, 5 by 9, right? Yeah, so into 2 will be 2.5 by, yeah, so I can see that this will be 5 by 9, right? So mole fraction of nitrogen is 5 by 9, mole fraction of argon will be what? 1 minus 5 by 9, 4 by 9. But yeah, we need partial pressure of nitrogen alone, right? So total pressure was 27 into mole fraction of nitrogen, we got it as 5 by 9. So this you can see is 3 into 5, which is 15 bar, right? So yeah, of course, we are looking for our correct answer here. We already have calculated it. We got obviously the answer to be equal to 15 bar, which is our B option. So what do we see here? Let's read the question. It says, which of the following has the maximum number of atoms? This is one of the simplest questions. One of the first questions that you come across when you are studying chemistry as well, the 11th standard physical chemistry based question. Logic alone should have been sufficient to solve this, but yeah, we can still calculate also, right? So yeah, it says the options are 1 gram magnesium, 1 gram oxygen, 1 gram lithium and 1 gram of silver, right? So atomic masses are given for all of these. We have to find out the maximum number of atoms. right? So let's try to calculate the number of atoms. How do we find the number of atoms? Whenever weight of a substance is given, right? So we can divide that weight by molar mass to get the number of moles. Once you know the number of moles, we can multiply that by Avogadro's number to get the actual number of particles, right? We know this number of moles is weight divided by molar mass, and what is actual number of particles? Each mole corresponds to Avogadro's number of particles, Na, or 6.02 into 10 to the power 23. So when we multiply number of moles by this number, we should be able to get actual number of atoms. Thing is, we don't even have to get the actual number of atoms, because if number of moles is more, number of atoms also has to be more, right? So it's like saying if I have like 2 dozen banana or 1 dozen banana, then obviously 2 dozen is more than 1 dozen. I don't have to say, okay, 2 into 12 is 24 and 1 into 12 is 12, so 24 is greater than 12. I didn't have to do this. If number of moles is more, number of atoms also have to be more. But yeah, let's see. If I get the number of moles of atoms, whichever has the largest number, that is my answer here, right? So yeah, what do we know? Mole represents a standard quantity. It's the fundamental unit for counting in chemistry. Mole represents 6.02 into 10 to the power 23 particles, right? So number of moles can be obtained by dividing the given mass by the molar mass, and number of particles, actual number of particles of the species, is number of moles into Avogadro's number. We have seen both of this. Let's go forward, right? So applying this in the given question, we were given the weight of all the things that were given were 1 gram, right? So easy calculation as well. Number of moles will be what? 1 divided by 24 gram per mole magnesium, right? So actual number of atoms will be how much? Into Avogadro's number. So 1 by 24 into Na, for the sake of ease. I don't want to calculate exact number, it doesn't make any sense. So let me just write it as this, right? Now going to oxygen. Oxygen is in molecular form, right? So oxygen is in molecular form where the molar mass is 32 grams per mole. So if I look at the actual number of moles of oxygen, right? So I can say that it will be 1 by 32 moles of oxygen molecules, right? Now each if you are looking at the number of oxygen atoms, each molecule has two atoms each, right? So number of moles of oxygen, when I write small n and this, I mean number of moles of oxygen. This is 1 by 32, but number of moles of oxygen atoms will be double of this. So 1 by 32 into 2, which is 1 by 16, right? So number of moles of oxygen atoms is 1 by 16. So number of atoms of oxygen, you can say, is 1 by 16 into Na, right? So 1 by 32 is your number of moles of oxygen. Number of moles of oxygen atoms is 1 by 16, and actual number will be 1 by 16 into Na. Let's go forward. Lithium also, we had 1 gram. So number of moles will be 1 divided by lithium, 7 grams per mole, right? So 1 by 7 moles of lithium atoms are there. So number of atoms of lithium will be how much? 1 by 7 into Avogadro's number. Similarly, in silver, we had 1 gram, and gram atomic mass was given to us as 108 grams per mole. Molar mass is 108 grams per mole. So 1 divided by 108 is number of moles of silver, and actual number of atoms will be how much? This into Avogadro's number. So 1 by 108 into Na, right? So think about all of these. So you had like what? 1 by 24, 1 by 16A, 1 by 7A, and 1 by 108A. Obviously, numerators are all the same. Numerators are all the same. Whatever is the larger denominator will give me the smallest answer, and whichever has the smallest denominator will give me the largest answer. I am looking for the largest number, so this is my answer. If smallest was asked, I would have said silver. Largest is going to be lithium. Just keep in mind this thing, that whichever is the lightest element, right? Lightest element in terms of molar mass, for the same weight, it will have the maximum number of atoms, right? So same weight, 1 gram each. Lithium is the lightest metal here, so it will be the one with the largest number of moles of atoms and largest number of atoms. If I had to put them in an order, this is the highest. First will be this, second will be this, and third will be this, and the least will be this, right? So yeah, of course, here we were only asked about the maximum number of atoms is there in which of these. So looking at the option, what do you see here? Of course, our correct answer is going to be our 1 gram of lithium, which is our C option. Okay, so let's go to the next question now. What does it say? It says the correct option for the expansion of an ideal gas for the free expansion of an ideal gas under adiabatic conditions is. Very simple question based on adiabatic free expansion. You know, one of the simplest cases where there is no calculation, nothing. So we have been asked about Q, delta, T and W, right? In all the options, we are discussing heat, work done and change in temperature, right? So what do you mean by adiabatic free expansion? So first of all, what is adiabatic? We know adiabatic process is one where there is no heat exchange between system and surroundings, right? Then what is free expansion? Free expansion is expansion against vacuum. When a system is not faced with any external pressure. So let's say there is this box that is there, right, in which there is a gas, and above this box there is a region, right, where it is perfectly vacuum, right? So there is no gas there. And if I suddenly make a hole here and allow the gas to expand into this vacuum, then we can say that this is free expansion. Basically, the idea is that there is no P external in this particular case, right? So what we say that P external, if it is equal to 0, we speak about free expansion. And if this process is happening adiabatically, that is no heat is gained or lost by the system, then we call it as adiabatic free expansion, right? So yeah, what is adiabatic? Heat can neither enter nor leave the system, and because Q is equal to 0 from first law, what do we know? Delta U is supposed to be equal to Q plus W, or du in terms of small changes, du plus dq plus dw. So your dq is 0 or Q is 0 in your adiabatic process, so du will be equal to dw, or delta U will be equal to work done in the process. Now think about this. As far as free expansion is concerned, our P external is 0, right? So we say that work done is supposed to be equal to integral of minus P external dV, right? So what is written here also, you can see integration of minus P external dV is going to be your work done. But since it is free expansion where P external is equal to 0, you can say that dW is also 0, and integral dW is obviously is going to be 0 because there is no work done. So we are going to see integral dW to be equal to 0. No work is done in the process. Gas is not facing any opposition. Gas can expand freely. So obviously no work is done by the gas, right? So we say that work done is 0, which means our delta U will also be equal to 0, right? So there is no change in your internal energy, right? So it is expanding against vacuum, and you can see here a vacuum is maintained here and the gas is allowed to expand slowly. Of course we have to have a massless lid and all. If the lid itself has a mass, then that is P external, right? So yeah, point here is that we just got that work done is equal to 0 because P external is equal to 0. P external being 0, your delta U will also be 0 if it is adiabatic. But what do we know about delta U? Delta U is like a measure of the, a change in delta U is an indicator of change in temperature of the system, right? So when you so what was shown here, as you can see, is the so what is shown here is that originally the gas was confined in one compartment, the other compartment was vacuumized, and when you allow the gas to expand into it, this process is called free expansion. And because everything is 0, you can say that change in temperature will also be 0. Why? Because your delta U is always going to be, NCV molar delta T, right? So NCV molar delta T, this is a formula I want you to remember, right? This is absolutely useful. This comes handy at a lot of places. NR upon gamma minus 1 delta T. You can write this also, or you can write P final V final minus P initial V initial upon gamma minus 1. These are all the three formulae that I want you to write down and remember, right? Very important. So as far as delta T is concerned, it is equal to 0. So we can say delta U is 0, so obviously N and CV molar, right? Molar, heat capacity under constant volume, these are not 0, right? So obviously the only thing that can be 0 is delta T. So we see that temperature does not change. P final, V final, P initial, V initial, all of these are the same. Q is 0, W is 0. That is why this is one of the easiest cases, right? Adiabatic free expansion, everything is 0, right? So delta H is 0, delta U is 0. The only thing that is non-zero is entropy. I hope you remember that, right? So looking at the options here, what are we looking for? We are looking for the correct option. Yeah. So the correct option when we are looking at an adiabatic free expansion is going to be what? Q is 0, delta T is 0, W is 0, right? So in A, I could see that Q is 0, but delta T they said is less than 0. No, that will not happen. Delta T less than 0 means work done should be negative. Anyways, this couldn't have happened. All three of these couldn't have happened anyways together. But yeah, obviously our correct answer is D option, where Q is 0, delta T is 0, and W is also 0. Okay, now let's look at the next question. Let's read what it says. The number of Faraday required to reduce 20 grams of calcium from molten CaCl2 is, right? So this is from electrochemistry. This is based on that part of, electrolysis part of your electrochemistry chapter, not what we study initially. This is speaking about calculating the number of Faradays, right? So let's look at the options 2, 1, 3, 4, right? Simple calculation, simple answer is what we are going to get. So you have molten CaCl2, which you are, from which you are taking out calcium using electrolysis, right? So what is said is that 20 gram of calcium is what I managed to obtain. So how many Faradays were required? Obviously, for this we have to understand what is Faraday, what is Faraday's laws related to electrolysis and all, right? So Faraday's first law says that the mass deposited, right? So you are looking at electrolysis, you have two electrodes, one positive, one negative. Cathode is where reduction takes place, anode is where oxidation takes place. So you will be seeing your cations getting reduced, right? So cations getting reduced into metallic form, and you will be seeing anions undergoing like oxidation, most probably giving us some gas or something. And as far as our cation is concerned, here we were speaking about calcium, right? So calcium 20 gram got deposited. How many Faradays is the question? Simple question. But yeah, the first law says that the mass deposited of the substance during electrolysis is proportional to the amount of charge pass through the electrolyte. Simple, right? So what we are saying is that weight of the substance should be proportional to charge. Charge is what? Current into time, right? So you can say that in order to remove the proportionality, I can multiply by some constant, so K into I into T. Rather, we normally take this as what you call as Z, electrochemical equivalent, right? So W is equal to Z into I into T. This is what we are, right? Obviously, what will be Z? It will be the weight when 1 coulomb charge is passed, right? It will be the weight that is deposited when 1 coulomb charge is passed. So I into T, if it is equal to 1, which means current into time of charge is 1 coulomb, then the amount of substance deposited will be equal to your Z, which is called the electrochemical equivalent, right? So so electrochemical equivalent of substance into Q will give me my weight of the substance deposited. Now, before we go further, let's understand a little. So I have already spoken about this. W is equal to Z into I into T, current into time, and we don't know about the current and all of those angles. But yeah, what is asked is what is the total charge that was there in Faradays that was used up, right? So let's speak about this. What is this Faraday in the first place? Let me speak about this in the first place. So here what is happening is that you have molten CaCl2, in which Ca2 plus ions are going to go towards the cathode, get reduced and convert into calcium, right? So this is the reaction that is taking place. Calcium takes place. Calcium 2 plus ion takes up 2 electrons and converts into calcium atom, right? Now what is Faraday in the first place, right? So what we call as Faraday, there is a logic behind this. I'm going to explain it to you, right? Any M plus, right? Any M plus, I'm just considering M plus a monopositive cation for the time being. We will speak about other cations also, other charges also soon. But yeah, general idea, to understand the basics, this should be sufficient. So M plus an electron converted to M, let's say. This is the reduction, right? absorption of electron, right? So gain of electrons is reduction. So here M plus is taking up 1 electron. So if I had 1 mole M plus, it will take 1 mole electron and give me 1 mole of the metal, right? So the idea is, we say that, okay, 1 mole of this M plus cation will take 1 mole electrons, and 1 mole electron, what will be the charge? Na into charge on an electron, right? So this is going to be equal to, if you calculate the value, what you are going to get is called the Faraday, right? So 96485 coulomb roughly. So 6.02 into 10 to power 23 into 1.6 into 10 to power minus 19 is basically what we are doing. We get roughly, we take it as 96.5 kilo coulomb, right? So 96500 coulomb, we roughly take 96485, whatever. So this is what you call as 1 Faraday. The charge associated with 1 mole electrons is called a Faraday, right? Or if I had, like, let's say M2 plus, right? M2 plus would take up 2 electrons, right? Will take up 2 electrons. So if I have, let's say, half mole of M2 plus, it will need how many? Each needs 2 electrons. So half mole of M2 plus will need 1 mole electrons, and we will again get half mole of this metal, right? So 1 mole electrons will be associated with half mole if you are looking at M2 plus. What am I coming to? I'm slowly coming to the relationship between molar mass and equivalent mass. So be very careful here, right? So I took only half mole because I wanted to keep my number of electrons as 1 mole. I wanted to look at 1 Faraday, right? So what did I have? I had half mole of M2 plus, right? So if I look at the weight of this thing, can I say that weight of the sample will be half into molar mass, right? Half into molar mass of this metal M, right? M2 plus whatever metal is there, its molar mass divided by 2, right? And what is molar mass divided by N factor here? You know that it is taking up 2 electrons. So 2 is the N factor of this cation. So molar mass divided by N factor is actually equivalent mass, right? So the equivalent weight of this M2 plus is exactly what is going to react with 1 mole of electrons. This is what you have to remember. 1 Faraday of any substance will have 1 mole electrons, and 1 mole of electrons is always going to deposit 1 equivalent of the substance. 1 equivalent of substance is obviously molar mass divided by N factor. That N factor is the number of electrons lost or gained per ion. So when you divide molar mass by this number, what you are going to get is equivalent mass, right? So I'm sure you remember this also. Equivalent weight is given by molar weight divided by N factor, right? And N factor is number of electrons lost or gained per mole of the substance, right? So if I had, let's say for example, M3 plus 3 electron giving me M, if this was the case, then I would take 1 by 3 mole, so that 1 by 3 into 3 will be 1 mole electrons required again, and I'll get 1 by 3 mole of this, right? So if I look at the weight of this sample, what am I going to see? I am seeing molecular mass. Oh wait, let me write it as M only, right? So molecular mass, let me write it as molar mass MM, just for sake of reducing confusion. So molar mass divided by 3, right? Number of moles is 1 by 3. Molar mass into number of moles is weight. So weight I am taking is molar mass divided by 3. But we know this is equivalent weight, right? So equivalent weight is molar mass divided by N factor. So for M3 plus, molar mass divided by 3 would have been my equivalent weight. So when I took 1 equivalent, I needed 1 mole of electrons. So for 1 equivalent of any substance, 1 mole of electrons will be required. 1 Faraday of charge will be used up, right? So here, what was given to me? I was given that I have 20 grams of calcium that was deposited. So if I want to find the number of moles of calcium, I can say it is given mass by molar mass, which is 20 by 40, which is half, right? So I have half moles of calcium. But from there, can I just get the the number of equivalents? No. What did I just realize? That number of equivalents of the substance deposited will be equal to number of Faradays, right? So I need to find the number of equivalents. I know number of moles. Now what the other relation I can use is number of equivalents of any substance is number of moles into n factor. So as far as calcium 2 plus is concerned, charge is plus 2, n factor is 2, right? So n factor of calcium 2 plus is 2. So I can say, okay, number of equivalents will be equal to half into n factor, which is 2, which means my number of equivalents of Ca2 plus, number of equivalents of Ca2 plus consumed or number of equivalents of calcium produced is equal to 1. So obviously what can we see here? One equivalent of any substance will react with 1 Faraday. So yeah, so by Faraday's law also you can go to this place, you can say that weight should be equal to Z into I into T. This is nice. Let me speak about this Z also. What is this Z? Think about this. As I was telling you, 1 Faraday 96500 is the charge that is associated. Unitary method, basic unitary method is what I'm using. Okay, so 96500 or 1 Faraday is what is associated with 1 equivalent weight. Right? So 1 equivalent weight of substance will be deposited by 1 Faraday. So how much is deposited by 1 coulomb is what we called as Z, right? So what will be deposited by 1 coulomb? This is what you call as our Z. So unitary method. Let's say 20 apples cost 1000 rupees. 1 apple costs how much? 1000 divided by 20, right? So same is the story here. So what I can say here is that from here, basically what we say is that we can cross multiply. We are trying to calculate this question mark. So I'll write question mark is equal to 96,500. Yeah, where? Question mark is going there, right? So yeah, a question mark will be equal to equivalent weight into 1 coulomb divided by 96500 coulomb, right? So the electrochemical equivalent that we are speaking about, this Z thing is going to be equal to equivalent weight divided by Faraday, right? So divided by 1 Faraday. Charge on an electron is what I was going to say, but yeah, 1 Faraday into I into T will give me the weight. Weight is already given to me. I into T was not directly given to me. The idea was that I had to find out the charge. So what can I say about charge? Charge will be equal to, or I can say charge will be equal to this into W divided by equivalent weight, right? So I into T is equal to charge is equal to W into 1 Faraday divided by equivalent weight. So W is 20 gram and equivalent weight is also 20, right? Equivalent weight is molar mass divided by n factor. So 20 by 20. So you are getting this to be equal to 1 Faraday, right? So the question was asking us about the number of Faradays that will be used up in this process, and atomic mass of calcium was given, and we were asked, we calculated that 1 equivalent calcium was deposited, which means 1 Faraday is going to be used up. So the correct answer is of course D option. Okay, so we had seen some questions today. We obviously will not be able to see the entire 15 questions from physical chemistry right away in this session, because I told you we will be discussing almost all the things in brief. At least all the concepts involved we will try to discuss as much as possible, so that we are not just looking at the question and the answer, right? So we have only seen a few questions here. If you ask me, were there like tough calculations? No. Was there any tough concept involved here? No, right? But the thing that you would have noticed is that all the relations, all the relationships, all the formulae and all were very useful for us, right? Like for example, the relationship between standard Gibbs energy and your equilibrium constant. Something that a lot of students do turn up, like, end up forgetting because, okay, this feels too complex, let me not go into details, right? Some simple questions were also there, like for example from Dalton's law, simple, calculate mole fraction, multiply by total pressure, get your partial pressure, like comparing the number of atoms. There couldn't be an easier question, right? So as far as NEET is concerned, the questions are never that tough. It's just that you have to, like, avoid mistakes as much as possible. You will have to not make a mistake anywhere. So you have to observe, give time to physical chemistry questions. Calculation intensive also can happen, but here we did not have any super tough calculations anyways. The point here is that conceptual clarity is very important. Understanding basics is very important. Give it time. Don't rush through it. Don't make mistakes. You will come out good. Right? So there are a few questions remaining. We will see that in the next session. This is Abhilash signing off. Best of luck. I hope you had fun. See you soon.